Hello, everyone, and thank you for joining us for the first online educational event of the year for surface measurement systems. Today, we'll be exploring the topic of battery electrode active materials characterization, and we're incredibly lucky to be joined by Joanna Siegesch and Dr. Annette Condor to explore today's topic. Just before we get into the presentations proper, I just wanted to highlight that there will be a question and answer section at the end of today's session, and you can take part in this in one of two ways. You can either submit your questions in the questions panel, you will see in the control panel to your right, or you could raise your hand during the session, during the Q&A session, and I will unmute your microphone so that you can ask the question yourself over your mic. This may be especially useful for people who maybe have an extended or two-part question if you want to actively discuss it a bit more with the speakers. So once again, please submit your questions as we proceed through the presentations in the questions panel, or raise your hand at the end. To kick us off today, we'll be going to Johanna Siegesch from the Helmholtz Zentrum Dresden-Rosendorf, more specifically the Helmholtz Institute Freiburg for Resource Technology. Johanna is currently in the process of finishing her PhD this year, so we're very fortunate to have her here today to share her insights with us. And then after Johanna, we'll go straight to Dr. Condor, our very own resident absorption science specialist with a specialization in inverse gas chromatography and dynamic vapor absorption, who will be able to take us through the rest of the presentation. So without further ado, I will hand over to Johanna.
Yes, thank you very much. I just need to share the proper screen. Okay. I hope everyone can see the screen now. Perfect. Okay, so thank you very much for the nice introduction. Yes, as he already said, I'm from the Helmholtz Institute Freiburg for Resource Technology. And we belong to the HRDR, so the Helmholtz Zentrum Dresden-Rosendorf, which is situated in Dresden. So we are situated in Eastern Germany, but especially the Helmholtz Institute is situated in Freiberg, which is a rather small town with roughly 40,000 inhabitants, also in Eastern Germany, very close to the Ore Mountains, because for us, we work along the whole value chain. So we have different departments from exploration, analytics, processing, of course. So basically everything that is close to resources and raw materials. So that's why we are situated in Freiberg, because here we also have one of the oldest mining universities in Germany. Yes, so the Freiberg is really the place to be when you work with in mineral processing, let's say that this way. The work that I'm going to present to you today is not only from myself alone, but also from my colleagues, Anna van der Bruggen and Martin Rudolph. Okay, so first, I want to show you the battery structure. So on the left, you can see a common battery. Then one picture more to the right, we have pyrolyzed this battery to get rid of mostly all these hazardous electrolytes. And then you can see a vertical cross section. So basically we cut it in half and you can see the cross section, which is embedded in an epoxy resin. And if we then zoom a bit more into the battery, you can already see these straight lines, which are the electrodes. And if we then zoom a bit more, then you can see the electrodes. We have a cathode active material and an anode. They are separated. Also covered with an aluminum foil and a copper foil. And in case of the anode material, usually we use graphite. But for the cathode material, there are different compositions possible. So, for example, we have NMC, which would be nickel manganese cobalt oxide, but also LCO, so lithium cobalt oxide, or a rather new material, let's say it this way, is LFP. So this would be lithium iron phosphate. But there are many other composites possible. And yeah, if we then zoom in a bit more, then on the left, you can see a structure. So the blue particles would be the electrode active particles from our cathode. And the tiny black dots that you see, this is the carbon black. So this is really, really fine carbon in a nanometer range, which is covered, or basically the electrodes are coated with this to increase the conductivity. And then you also see like an orange shade surrounding the particles, which is the binder, which basically is used to hold everything together. For example, here there's PVDF used, but there are also other binders, commercially used in the industry. So basically, from all of this, you can already see the battery is quite a complex composite structure, especially the cathode materials, but also because we have organic material, we have metals, so we have all of this together inside the battery. So also for the recycling, it's quite a challenge. Yeah, so why do we want to recycle the batteries? Maybe I don't need to ask these questions anymore because over the last months and years, it's became more prominent. Also with electric vehicles and everything, that we really need to recycle the batteries in order to recover all of the valuable metals that are inside a battery. So here on the left, you can see a diagram which shows the supply risk versus the economic importance, which is basically came up from the European Commission. And you can see especially the graphite and the cobalt are critical raw materials. But also this report is by now a few years old, so even the other ones, all of them become more critical because the demand is increasing. Yes, here we have a composition of a battery in percent. So you can see we have almost 20% of the anode. So in our case, the graphite, then the lithium metal oxides for the cathode. Here we have up to 27%, and then we also have quite some amount of copper and aluminium inside the battery. So when you just look at these different materials, we have over 60% of the batteries are valuable and critical resources. So in order to really keep up the good work that's been established with the electric vehicles and everything and the green transition, we really need to recycle these the batteries. Okay, so how do we do this in our department in Freiberg? So we focus mostly on a separation technique called froth flotation. Of course, there are many other separation techniques for mineral processing, but in our case, we focus on froth flotation, which separates the particles according to their difference in wettability. So there are particles which are rather hydrophilic and they really like to interact with water, and there are particles which are hydrophobic and they do not like to interact with water. So if you put all of these particles in a huge tank, as you can see here on the left, usually you have a rotor-stator system, so you have a lot of turbulence and mixing going on, and then you add air. Then the air, the bubbles, will be very finely dispersed, and they will collide with the particles. And the particles, which are rather hydrophobic, will attach to the air bubble. They will rise to the top, and then you can collect the froth. And basically, then you have your concentrate, or in the case of the batteries, we would call it the overflow product, which would be the graphite. And we have the underflow product, which are the cathode active materials, because they would stay in the suspension. And this is how we would separate the graphite from the metal oxides. Of course, in most cases, especially in mineral processing, the desired material that you want to float is not the one which is hydrophobic. So this is why we have a huge playground of reagents. We use surface active collector molecules, which attach selectively on certain minerals and make them hydrophobic. So, and because the whole process has a lot to do with surface properties, and also in general, for any kind of separation of materials, you really need to understand the particles and the material that you're working with in order to be able to really successfully and effectively separate them. sorry. Yes. So here are the materials we are working with. For the cathode electrode, we have the LCO, the NMC, and the LFP. And for the anode electrode, we have the natural spheroidized graphite and the synthetic graphite. And on the bottom right, you can see a particle size distribution. So you can already see that for the D90, they are all below 30 microns, so they're all quite fine. I'm so sorry, I'm a bit sick. Yeah, really sorry. So the LFP is much, much finer than the LCO and the NMC, whereas for the graphite, they're mostly in the same size range, but the shape is very different. And also for the NMC, you can see it's much rougher than the LCO. I'm so sorry. Okay, so now I come to the characterization techniques that we're using. So I'm really sorry. Yes, so I want to start with the IGC. Here, of course, in cooperation with surface measurement systems, we use the inverse gas chromatography to analyze the materials for their surface energy. And here you have the particles inside a glass column, and you send through known probe molecules. And according to the interaction of the molecules with the particles, you get information on different physical-chemical parameters. Sorry, properties. We also use the Washburn method. Here you have a glass tube where you put your particles inside. You have a frit at the bottom, and when you put the frit in contact with water, the particles, if they're hydrophilic, they take up water, and the water uptake is measured, and from this you can get contact angles, and via the contact angles you can also get kind of a surface energy values. We use the optical contour analysis method, where you have, in our case, there are different methods or conditions how you can analyze this. But in our case, we had a tiny glass vial where we had water inside. We put our particles, attached them to the ground. We could put a gas bubble on top, and we measured the contact angle. Yeah, sorry. So the last three methods were more focused on only one parameter, so surface energy or contact angle. But we also did a few studies where you have a bit, where more particle properties come into play, let's say it this way, and which is a bit more realistic in terms of flotation. So here we have the particle bubble attachment, where we have a syringe. Also, again, in this little glass vial filled with water, we have our suspension inside. We create a gas bubble at the end of the syringe. We stir the particles. After some time, we stop the stirring, we let everything settle, and then we analyze the amount of particles that is attached to the gas bubble. And we also have some analytic particle solvent extraction tests. So we have a separating funnel with two phases. In the bottom, you have the aqueous phase, and in the top, you have the organic phase, in our case, cyclohexane. You disperse the particles inside, you let it rest and wait for the phases to separate. And afterwards, after the phase separation, you can see how many particles transferred to which phase. Okay. First, I need to drink something, sorry. Okay, first I want to start with the contact angle measurements using the Washburn method. So here on the left, you have an actual picture how it really looks in our lab. So you have this little gas tube where the particles are inside. This is not the battery material, which is usually very black. So this is a different kind of material, but just to get you an idea how it looks. So the white thing, that's the particles, and then it is dipped into water, and depending on how much water is taken up, you from this after evaluation you get the contact angle. So for the LCO, we got a contact angle of roughly 50 degrees, but for the NMC, we were not able to get a proper contact angle because we had some problem with the packaging, which is probably due to swelling. So after the evaluation, we saw that the data set, let's say, it's not meaningful for the evaluation. So here, unfortunately, this didn't work and we didn't get a contact angle. And for the graphite, we can only say that we have a contact angle above 90 degrees. This is a slight drawback of the method, because in theory, everything below 90 degrees hydrophilic, everything above 90 degrees is hydrophobic. And of course, that graphite, if there's no water uptake at all, you can only say it is hydrophobic and it's above 90 degrees, but you cannot, you do not have an exact contact angle. So it could be 90 degrees, it could also be 150, we don't know. These are the results with the optical contour analysis. So as I said, we have the particles on the bottom. We place a gas bubble on top. And for the LCO and the NMC, you can really see the gas bubble does not really want to interact with the particles. It really stays at the syringe. We get contact angles of 14 or 15 degrees. So really, really hydrophilic. But for the graphite, you can see already that the bubble is attached to the graphite, and we get a contact angle of around 140 degrees. So here you could really say, according to these contact angles and the definition of the contact angles, that the graphite is hydrophobic and the metal oxides are hydrophilic. So if we just look at these contact angles, the separation should be very easily done because we have really high difference in wettabilities. But of course, in a lot of cases, this is in theory not the case. Because if we want to now look into a real battery, because these were all the pure materials. So if we now get into the real battery as a composite material, here there's a picture where you can see the NMC particles all agglomerated, and they're surrounded by the binder. So the yellowish so the yellowish color and shade, that's the binder, which is surrounding all these NMC particles. And if we now do the contact angle measurements again, here you can already see we have a contact angle for LCO, which is coated with a binder of 75 degrees, and the graphite coated with a binder is 81 degrees. So here you can already see that this really nice difference that we had before for the pure materials is basically gone. And yeah, this is all due to the binder. So the binder makes the more hydrophilic particles more hydrophobic, and the more hydrophobic particles more hydrophilic. And this really is a problem. So one really crucial step for the flotation is the pre-processing to remove the binder. Otherwise, yeah, this will not work. But of course, there are also other challenges. So if we now come back to the pure materials, so just the pure NMC, just the pure LCO, pure graphite. Here, as I said, we did this extraction test where we had the two phases. So according to their wettability, if they are rather hydrophilic, they would transfer to the aqueous phase. If they are rather hydrophobic, they would transfer to the organic phase, in our case cyclohexane, and the aqueous phase is just tap water. Then according to the contact angle measurements we just saw for the pure materials, we would expect the graphite to go into the organic phase and the metal oxides to go into the hydrophilic phase, because I mean contact angles of 14 degrees, those are really, really small. So they really show hydrophilic, they should show hydrophilic behavior, let's say it this way. But if we have a look at the results that we get, we can see that almost all of the material, regardless of which material we are using, goes to the organic phase. So this is rather a contradiction, let's say, to the results of the contact angles. But for this method, what I was saying early on when I introduced to you the different techniques, here also other particle properties come into play. So the behavior of the particles at the interface is not only determined by the contact angle, but also by the particle shape, by the particle size, porosity, roughness, and there are a lot of other factors that we have to include here in order to explain this behavior. So for example, if you have a look at this small image, for example, here we've just put some NMC powder into water, nothing else. And I hope you can all see it, it's very tiny, but there are gas bubbles on top of this, on the material, on the NMC powder. So here we also see that despite it is rather hydrophilic in terms of contact angles, we assume due to the very rough surface, what you have seen of the SEM pictures, we do not have a complete wetting of the particles. So this is also another factor. So here you really would have to make sure that the particles are wetted completely in order to really have this hydrophilic behavior. Okay, so now I want to come to the IGC results. So as I said before, the IGC, it's a gas probing technique. So we have this column, and inside the column, we have our particles that we want to analyze. And then we send different probe molecules through the column. And depending on the interactions of the probe molecules with the sample, we can then obtain information about the surface energy. Of course, there are different other, there's a range of other parameters that you can also extract, like Hansen solubility parameters, work of adhesion. But in our case, we are focused on the surface energy because, as you can see on the image on the right, there's it's not a direct correlation, but the trend is in a way that with increasing surface energy, the surface becomes more wettable. So if you now think in terms of contact angles, if you have a low surface energy, you have very high contact angles, and the surface is not easily wetted by water. And if the surface energy is increasing, the wettability is increasing. Yes. For the surface energy, we have a total surface energy of the particles, but the total surface energy is made up of a dispersive component and a polar component. And in order to analyze or obtain those two different components, we use different probe molecules. So for the dispersive part, we usually use alkanes. Yeah, so the common ones would be, for example, hexane, heptane, octane, nonane, decane. For the polar parts, there are also different molecules used. In our case, we use ethyl acetate and dichloromethane to obtain the Lewis acid and Lewis base component, which make up the polar component of the surface energy. Yes, and we can also obtain information about the heterogeneity of the sample in terms of surface energy by changing the quantity of the probe molecules that we send through the column. So we can only send very tiny amounts, and we can send a huge amount of molecules over the surface that can interact then with the particles, and this gives us information about the heterogeneity of the surface. Okay, so first I want to start with the surface energy results for the cathode materials. So here on the top, you just see again some information on the measurement. So we used the finite dilution condition. So we changed the quantity of the probe molecules, the amount. In order to get the distributions, we measured this at 100 degrees, and the calculation were done with the Dorison-Gray method and the Della-Volpi scale. Yes, the probe molecules I already introduced to you. And yes, here you can see in the graph the results. So we have these distribution curves for the surface energy, for LCO in blue, NMC in green, and LFP in red. And on the left, rather for the lower values, those are the polar parts. And then on the right side, middle right side, you can see the dispersive part and the total part of the surface energies. Yes. So what you can see here is that LFP in red has the lowest total surface energy, and it is the most homogeneous because it has the narrowest distribution. Whereas for NMC, it has a really wide distribution of surface energies and also the highest total surface energy with roughly 150 millijoule per square meter. Also very interesting is that the dispersive part, so if you check the maximum value of the LCO, NMC, and LFP for the dispersive part, for all of them, it is usually, or it is around 120 millijoule per square meter. So the dispersive part is rather similar, whereas the polar part, here we have a significant difference. So for the LFP, we can say that the polar parts is almost, it is neglectable. Whereas for the NMC, it has a quite high polar part with almost up to 30 millijoules per square meter. So there's a significant difference in the polar surface energy components between the cathode active materials. If we now have a look at the anode materials, so we have the natural graphite and the synthetic graphite, you can already see also on first sight, there's a huge difference between those two materials. So the natural graphite in grayish colors, here we have a very, very homogeneous surface, so there's almost no distribution at all, whereas for the synthetic graphite, we have a huge or large distribution, and also the maximum surface energy value is really different, with 120 for the natural graphite and then roughly 170 for the synthetic graphite. And also for the polar parts, there's some deviation there. Of course, if we have a look at the graphite, the most reasonable explanation for the difference is the different processing route. So the synthetic graphite is usually obtained from raw materials like petroleum coke or coal tar pitch, and it goes through a lot of different processes, so also very high temperatures for the graphitization to finally end up with a synthetic graphite. Whereas the natural spheroidized graphite is usually recovered from a real graphite ore, which is then recovered after mining and the flotation process, and goes basically through the spheroidization to get these what we call potato-shaped graphite particles. So this is a very different treatment for the material. So and which we can actually see here in the surface energies. If we now have a look at both of them, so on the left we have the cathode materials, on the right we have the anode materials again. We cannot really say there's a general trend, because as we can see, the graphite is so different. We cannot say that the anode behaves like this and the cathode behaves like this. It's more of a complex story, let's say it this way. What we can, maybe like for the polar surface energy components, there are a bit higher for the cathode materials, but also here we have the LFP with almost no polar components. So it's really hard to deduce anything from the surface energy. So you really need to see the whole picture at the end. Okay, so this is again the surface energy obtained for LCO, NMC, and the natural spheroidized graphite, just for those three components. Now as a bar chart, and a bit different visualization. So we have the dispersive part in blue and the polar part in orange. This is for comparison reasons, because with the Washburn method I told you, we can also extract the surface energy from there with the OWRK method. So here we have the values for the surface energy from the Washburn analysis, and I find it very interesting that the values are so different. Here we could say, yes, this could be possible because the measurement temperatures are very different. So for the IGC, these measurements were done at 100 degrees, whereas the Washburn method is done at 20 degrees. So we have a huge temperature difference, which really influences also the surface energy. But this Annette will show you a bit more in more detail later on. Sorry. But I want, oh, I'm so sorry. But what I found even more interesting is, sorry, that I'm really sorry. That not only the final values, but also the different components are completely different. Okay, sorry. So for the IGC, we get the natural spheroidized graphite with the lowest polar component, and the NMC with the highest polar component. But for the Washburn analysis, we get the NMC with the lowest polar component and the LCO with the highest polar component. Sorry. Yes, So even though we have these different temperatures where we could explain the final total surface energy values, but I would have at least expected that that the tendencies within the materials regarding the dispersive and the polar part follow the same trend, which we have not. So basically here also another message from my side, you always have to be very careful when comparing values that you got from different techniques. So on the one hand, we have the IGC, which is we have a dry powder, but it's a gas probing technique. So you really have this molecular interactions of the probe molecules with the particles. Whereas for the Washburn analysis, we also have a powder bed, but you use water as a bulk. So you have a liquid covering a large surface. I'm really sorry. Yes, on the other hand, for the IGC, because in both cases, we do not get the surface energy directly. So we always get it indirectly by calculations afterwards. What we actually measure from the IGC is the retention times of the probe gases. And for the Washburn analysis, it's the penetration times or the water uptake. So, and after the calculations, there we then finally get the surface energy. But the actual data that we measure is very different. Yes, and also what I said, the temperature is also very different. So it's, we really have to be cautious and careful when comparing results that we get from different characterization techniques. Okay, now I want to come to the particle bubble attachment. So again, we have this little setup. So the left picture, you can see this is how it looks in our lab. So we have this tiny glass vial filled with our suspension. We have the syringe from the top where we create the gas bubble. We have the particles. We stir the suspension, and after ending the stir, we let everything settle, and then we can analyze the surface or the bubble loading, how much percentage of the surface of the bubble was covered with particles. So, and here you can see the bubble loading in percent for the NMC on the left, and for the right it's the graphite. And as you can see, although we have this huge difference in contact angle, again, we have, just like for the extraction test, we have a very similar behavior now when it comes to the actual behavior at the interface and in the process. So for both of them, we get roughly 25% of particles that are attached to the bubble. But here, as I said, the good thing in our case is that we have a lot of reagents to play with. So as soon as we add a selective reagent, in our case Ascade, you can see, although the NMC bubble loading is also increased by a bit, so now we are at a bit over 30% for the NMC, but for the graphite, we really, we increased to 100% bubble coverage. So here, the Ascade interacts with the graphite particles and really enhances the hydrophobicity. But of course, we have to be really cautious, because even though a lot of people are stating that the metal oxides are hydrophilic, they still form stable attachments to an air bubble, even without adding any kind of reagents. Okay, so we also did some real flotation tests. Here we can see the recovery in percent. So we have the graphite and the NMC, again, without reagent in blue and with some reagent in orange. And here again, you can see that when using the Ascade, we have a recovery of graphite above 80%, which is really nice. For the NMC, we do have some recovery, which is probably due to, there can be many reasons. So one reason, of course, it could be due to what we call true flotation. So the particle actually sticks to the bubble and rises to the top. We can collect it as a froth. Or we have mechanisms, what we call entrainment. So in the graph, you can see entrainment in the froth when the particle is not attached directly to the bubble, but it's rather in the lamella, so where the liquid is inside the froth. Or, for example, it could be entrapped inside the graphite agglomerates, because I don't know if you saw it, but on the previous slide, the graphite was quite agglomerating. So as we have a lot of fine particles, the NMC could also be entrapped inside these agglomerates. So what is very important is to properly disperse the conditioned black mass, also to really wet the NMC. What I showed you earlier on, we have these tiny gas bubbles on the NMC particles. So it's really, the pre-treatment is really important in this case. Okay, so now I come to my summary and the outlook. On the right, you can actually see a proper flotation or lab flotation cell in our case. So you have this froth on the top, which is scraped off. You collect it as the concentrate, or this would be the overflow product. And you have here some SEM images. So the top one is the feed, where you have the mixture of the cathode active materials and the graphite, and then the overflow product. You have mainly graphite, and the underflow product, you have a lot of NMC and LCO. So basically, one of the main points that I'm working on is that you really have to understand the particle properties in order for successful separation, even though in the case for the battery materials, we haven't understood everything yet, but research is always ongoing, so there are a lot of things we have to uncover. Also, the good thing is that the process actually works. So now we want to understand how everything is working. Also very important, usually in mineral processing, especially for flotation, a lot of people rely on the contact angle. That's why a lot of people stated that the metal oxides, they are hydrophilic. And of course, if you just look at the contact angle, they are hydrophilic, and the graphite is hydrophobic. But just one single value is not sufficient. So you cannot only take the contact angle, you can also not only take the surface energy. You know what I mean is you always have to have a look at the broader picture, and then then you really can describe the particles. Of course, the lithium metal oxides, they are less hydrophobic than graphite, but of course, as I just said, they cannot really be considered hydrophilic in total, because of course even them being hydrophilic, as people say, they still attach to the gas bubble and they are still recovered. So and this is just for the pure materials. So I showed you at the beginning, if we set the binder on top, this is even worse. So the binder removal is very crucial if you want to successfully separate the particles. Then so flotation, I only showed you one reagent, but usually in the flotation you have a frother, you have a collector, which renders the particles hydrophobic. You also have depressants, which render other particles hydrophilic. So you have a lot of chemicals and reagents in there, and a lot of interactions which are really complex. You also have the hydrodynamics. You have a suspension phase. You have a froth phase. So it's really a complex process, and there's a lot of research going on in that field. And of course, one topic, especially for the batteries, it's really like for the anode, it's usually the graphite doesn't change too much, although also here we have these different types of graphite. But especially for the cathode side, here we have a really complex composition with all these different materials possible, NMC, LCO, now LFP. And there's so much research going on, and it's really, really complex and a really tough task then later for the recycling, because you cannot treat all the different things the same. So basically, in the worst case, you have to, for all the different things, you have to find an individual processing route. Yes, so there's a lot to do from our side. I hope I could show you a few interesting things. Of course, if you have questions, always contact me, contact Annette. I'm very happy to answer all your questions. Here are also some of our latest publications in the field of battery research, but also on the field of particle characterization, also ultrafine particles, many different publications. Go have a look at them. If you could also text me, send me an email, and I could forward them to you. So just feel free to ask. And with this, I'd like to finish my presentation, and thank you very much for your attention.
So I will just continue with the with the characterization of these materials, what Johanna introduced, and I will not show them again. So first I will show you some DVS results, and then some surface energy data and why the surface energy is important. And at the end, I will show you an interesting case study on the interfacial interactions in solid-state batteries. The DVS instrument, what we used to measure the water sorption and the cyclohexane sorption of these different battery materials. The aim was to understand deeper the separation process, the wettability results, what Johanna got, and also in order to improve these processes or the separation process. And the DVS system is basically a gravimetric technique. So there's a balance. On one side, we place the sample, and then we introduce the different percentage of humidity or cyclohexane concentration. And at each steps, we rate how much the sample absorb. And once we reached the saturation, the 90%, we decrease this concentration and we measure the desorption. So at the end, we can get desorption curve from the data. And we measure the water sorption of these lithium metal oxides and the graphite sample. So first, here's the water sorption curve at 25 Celsius of lithium cobalt oxide. You can see the water uptake is quite low. And seems after the desorption, the sample message goes back to the initial. So it's a reversible process, this water sorption. In case of the NMC, what we saw, it has much higher water uptake compared with the lithium cobalt oxide. So 10 times higher water it can absorb. It has higher affinity to absorb, attract water. And the sorption is not reversible. So it's irreversible. So there's some water which remain on the surface. And in case of LFP and pyrolyzed graphite, we already could measure the cyclohexane sorption-desorption curve. And you can see that LFP and pyrolyzed graphite, so LFP is on the left side, on the right side, the pyrolyzed graphite. So you can see that both samples seems has a higher uptake with the cyclohexane, and the water is quite small, especially in case of the pyrolyzed graphite. And seems they has better affinity with cyclohexane, bit organic. And that's basically supports the separation data what Johanna got. And we also have the data already also for LCO, the lithium cobalt oxide. And since lithium cobalt oxide has a very low cyclohexane take mass in percentage, it's a mass percentage. So seems they are really seems more hydrophobic materials, which also supports the wettability test, the extraction process what Johanna did, but it does not support the contact angle data. These results are still in progress. So currently we are measuring the NMC cyclohexane absorption and desorption curve, and also after that we'll continue with the other samples to get really the whole picture about all the different lithium metal oxides and the different graphite samples. But so far, the DVS data shows similarity with the wettability test or the extraction. Just to summarize again the different components of battery materials, there's cathode, anode, separator, and electrolyte. And the battery performance depends of the energy density, power density, thermal stability also, which is quite important. And also everyone knows that in case of winter, the electric cars range is much shorter than during summer. So the temperature has really an effect on the performance of batteries. Also, the temperature can affect properties at molecular level of the battery materials. So there can be structural, physicochemical, electrochemical changes due to the temperature. Some examples for structural changes, so there can be volume change or gas transition, phase transition. Some physicochemical properties can also change due to the temperature. So surface chemistry, surface energy can change, electron density can be changed. So all these properties at molecular level, which are changing due to the temperature, probably affects the performance of battery materials at different weather conditions or different environments. And we think that maybe there can be a direct correlation between surface energy and the temperature effect on the performance of batteries. Because what is surface energy really? It's basically the willingness of the surface to react with the surroundings. Because atoms in the center of the material, they interact with each other, but on the surface they only interact towards to the center, and some surface electrons can react with the surroundings, and probably this affects the electron reactivity. The electron's reactivity affects the performance. Surface energy is a symbol is the same as the surface tension, gamma, and as Johanna mentioned also, yeah, it has different components, dispersive and specific. And the specific can be also divided for two components, the acid and the base, so the Lewis acid and base component. Solid state batteries become quite popular, and because it's safer, and there's no electrolyte, and there's no liquid electrolyte, which is very flammable. So battery materials, the market is going towards this direction. But there's a lot of challenges in case of solid state batteries. For example, to achieve homogeneous distribution of the different compounds, the solid electrolyte, the active material, and the carbon. And to achieve this uniform or homogeneous distribution, the interfacial interactions, so the surface energy, plays an important role. And also it helps also to see the compatibility between the different components, and also it helps to improve these materials future. So the results on the thermal stability at the moment, we just focused on the effect of the temperature on surface energy of these different materials. So first we investigated the graphite samples. So we had the natural graphite and the synthetic graphite. The natural graphite was from Sigma-Allogy, specially made for anode powder, especially made for battery application. And the mesophase graphite, it's from Institute. On this slide, you can see the dispersive surface energy of the natural graphite, and I will show you the surface energy profiles instead of the distribution graph, which was generated exactly from this profile, what Joanna showed to you, but it's exactly the same data set used. It's just a different demonstration. So in case of natural graphite, the surface energy is quite uniform, so not much distribution of surface energy at different temperatures. And also you can see it doesn't change much with the temperature. The specific surface energy is very low, as we expected. It's graphite, so that small specific part what we measure, probably it comes from impurities or just a almost like error of the measurement. Synthetic graphite surface energy clearly changed with the temperature. At the moment, we also measure the 120 Celsius of this sample. And this synthetic graphite is made from coal tar pitch, and it has also a heterogeneous surface energy profile. So it's not that uniform as natural graphite. And if we compare the two graphite samples, the synthetic and natural graphite at the same temperature, you can clearly see the difference. The natural graphite is more homogeneous energetically, while synthetic graphite is very heterogeneous energetically. Why is it important? Because if there's energy heterogeneity, so that if the surface is not uniform energetically, it can affect different processes and applications. So the flowability, processability of these materials, dissolution, dispersion is affected by this. So, and of course, the coating quality, because in that case, surface. So it's very important the heterogeneity of the samples. It has an effect on so many other things. On the next couple of slides, I will show you how the temperature affects the surface energy in case of the lithium metal oxide. So we measured lithium cobalt oxide, NMC, the nickel magnesium cobalt oxide, and LFP, the pure lithium iron phosphate. Lithium cobalt oxide surface energy clearly changing and increasing with the temperature. So the temperature has a huge effect on the surface energy of this material. NMC also changing with the temperature, increasing trend again. And so the surface properties of both cathodes are changing with the temperature. We have also, we measured recently just the lithium iron phosphate surface energy at 100 degrees C, and we compared with the LCO. And you can see that there's significant difference between LCO and LFP. As also Johanna mentioned, LFP has a very, very small specific surface energy, even smaller than LCO. And also it has a higher dispersive surface energy. So which means that the LFP surface polarity wettability is very low and compared with the LCO. This is what we also saw in case of the DVS results, that LFP shows better sorption behavior with the cyclohexane compared with the LCO, which seems has higher water uptake than cyclohexane. So this supports the data, what we got with the DVS. And just to compare all the different cathode materials at one temperature, it's 100 Celsius. And this is just the dispersive surface energy. I focus just the dispersive surface energy because I will show you on this slide the anode materials as well. You can see that, yeah, at infinite dilution, since they are very similar, as also Johanna mentioned, and clearly we could see from the distribution graph. There's a slightly difference in heterogeneity of these samples. And LFP has quite significantly higher, with higher concentration, finite concentration, compared with the LCO or the NMC. Anode materials, both the natural graphite and the meso phase graphite, has significantly higher dispersive surface energies than these materials. So you can see that they are not completely the same. As also Johan highlighted, there's not really similarity in the surface energy between them. The interfacial interactions in solid state batteries, this is a really important and high demand topic in research right now. And this graph is really explain all the different interactions between interfaces and the different components in solid state batteries. Also, there's a more nicer explanation of all these different interactions. So there's on the left side, you can see an uncoated cathode, and on the other side, you can see a coated cathode. When it's an uncoated cathode, there can be interactions between the solid electrolyte and cathode and carbon, and also the common types of interaction on the middle you can see. But in case of coated cathodes, there are even more different interactions. So the coating material and the solid electrolyte, and also the cathode and the coating on its surface. And if the coating is not complete, there can be, or imperfect, there can be a solid electrolyte and cathode interaction still. So it's very, very complex, as also Johan highlighted, and to really understand the effects and what's happening in the batteries, and also how these batteries can be improved and then also recycled. We have to measure and we have to characterize them, understand a bit more deeply the effects and what's the temperature can cause on these samples. Just to summarize what IGC can provide you if you are working on this field, research and developments of battery materials. So it can determine, or it can provide you comprehensive surface characterization of these materials. You can also measure the temperature effect on these properties, and also the humidity effect on these properties. You can get processing performance of these batteries, as you could see in case of the two different graphite, the natural and the synthetic graphite. The production route, the processing route is different, and it's clearly cause differences in surface energy and surface chemistry. And it's very, very important to see how big is this difference. You can also get with IGC system. Also, you can determine from the surface energy adhesion, cohesion, dispersion properties. You can predict how compatible the dispersion dispersion behavior, and finally also binder cathode compatibility. What you can also determine from these with this IGC system what we have. So before before we answer the questions, I would like to thank to my colleagues, to Helmholtz Institute, to collaborate with us, because it was a really interesting study so far, and it's still going on. It's really fascinating how the different techniques and how the different characterization show different properties of these materials and how useful are they. And also thanks to my to Armando and Connor, who's been running the DVS measurements, and Danielle Burnett also to his support and all the meaningful insights of this study. Thank you also for your attention and time, and we are happy to answer your questions.
Thank you very much, Annette. That was great. And another thank you to Johanna Sigash. So yes, just a reminder to our audience, you can now submit your questions in the questions panel in writing, or you can raise your hand and we can unmute your microphone so you can ask the question yourself. So just to kick us off.
Yeah, sorry, no, just to,
No,
I mean, sometimes people don't like to ask question openly. So of course you can also, I think I showed my email address, and it should also be somewhere on the advertisement. So in case there are any questions afterwards, just feel free to contact me. I guess the same as for Annette. I will speak for us both. So in case you have any questions afterwards, feel free to contact us, and we are happy to talk to you about, yeah, all of this. Because sometimes I often have questions coming in afterwards, because people were like, yeah, I didn't have time, or I didn't want to ask in front of the others, or yeah, so they're
yeah. I think I'm the same in that way. We have our first question here, and they have asked just more of a general thing about the instrumentation used. What is the maximum temperature used for the ITC column oven?
The maximum, yeah, the maximum what we used is 120, but the highest temperature is 500 Celsius, what we could use. But we didn't use in case of these materials the highest. So we went up with the measurements so far 120. We try to target now the lower temperatures to see the surface energy level at that temperature. So maybe it can be directly correlated with the performance of the batteries at different temperatures. So yeah, that's the temperature range.
Someone's also asked what kind of range you can get on the typical sample mass used in these experiments.
Yeah, good question. I think we used from 50 milligram to up to 150 milligram of these different samples. Of course, depending on the surface area of these materials, because we wanted to keep the measurements within a reasonable time frame. So if you use a lot of sample in the column to elute a solvent, it takes quite long, and we don't want to wait weeks. So, and also it's not good if it's too quick. So about 150 was the maximum sample amount, milligram. Yeah, I don't know, Johanna.
Yeah, I mean, it really depends on the material, what you are analyzing, and on the BT of the material. So yeah, because according to the BT, you also adjust the quantity of the probe molecules that you send over the surface. So as you can see on the diagrams from Annette, it just said something like 0.2, so that would be 20% of the monolayer coverage based on the BET of the particles, based on the area of the molecule that you sent over the particles. So it always depends a bit which particles you are analyzing.
Exactly, yeah. Yeah. Because also we definitely don't want to oversaturate the surface, so we focus on the interactions which occurs on the surface and with the solid, and there's no solid-solid interactions.
Yeah, so usually also like a net, usually we measure only up to like 20% roughly. Yeah, because afterwards, as you can already see, the diagram it's just flat. So afterwards, nothing really happens. So we usually, yeah, so we usually stop at 20% surface coverage. Yeah, but we also, I mean, there are different columns that you can use, like column with diameters. So depending on your material, also if it's finer or not. Yeah, so it's a bit, yeah, material specific, let's say. But the nice thing about IGC is that you don't need a lot of material. So yeah.
Great, thank you. Question here. They wonder if you've considered, and forgive my lack of scientific parlance, but they've said they wonder if you have considered the Li loss during the flotation process. How can this issue be overcome?
Yes, so that's a good point. That's actually something that we've also analyzed. So we saw a lot of the lithium is actually in the solution afterwards, and we have another PhD student, Eliza, who's her PhD is on exactly this topic. So she's analyzing the process water of flotation, and she's using methods like ion exchange or something. So it's more into the metallurgical hydrometallurgical route to extract the lithium from the process water after flotation. Yeah.
Thank you. Someone asks here, can we use any of these techniques to analyze the physical properties of thin film electrode sheets?
Yes, I mean, DVS or IGC can be used also for thin films. The size of the film, the IGC has a little bit limitation, but for DVS, we can measure, yeah, definitely.
The next question here, we have a written question, and then someone would like to unmute to ask a question as well. Reese Jones asks, what sort of technologies are used to coat cathode materials? Are these wet or dry technologies?
I must admit, I don't know. So we are more focused on the recycling, not on the battery production. So yeah, but yeah.
He wanted to know because you measure the contact angle in case of LCO and graphite.
I mean, in our case, for the contact angle in specific, we use for the pure materials, we just use the powder, the pure powder, and for the coated material, we use the wafer, which was coated with the binder. So we bought it this way. We didn't coat it ourselves. No.
Okay.
And now we have Monica Chowdhury, who would like to unmute her microphone and ask a question herself. So Monica, you can go ahead now.
Hi.
Hello.
Hi, Monica. Hi.
Hello. Ma'am, is it possible to utilize the waste material of lithium battery along with activated carbon for use for generation of current in future?
Sorry, you mean so the recycled material, if we could use again in the
Yes,
battery?
ma'am. Yes, ma'am. Recycling.
Yes. So yes, so the results I showed you here, it's just the pure materials really, but when it comes to the real batteries, so we have a lot of corporations also with industry, and there we have a really high recovery and also grade of graphite. So this and we have another Helmholtz Institute in Ulm, and they work with the graphite, and it's not directly my project, so I don't have all the details, but I know that we sent some of our recovered graphite to them, and they analyzed the graphite and according to the capacity and different things. So the battery itself, it's not so much my thing. I'm more into the mineral processing and the recycling. But they analyzed it, and it is almost as good as, let's say, the first used graphite. So we can really, in the future, let's say, because right now,
in
of course,
future, yes, ma'am.
Yeah, of course, right now it's all lab scale, but first tests are really promising, so that you can really have good recycling. And another one, I think I didn't mention, another plus if we extract the graphite from the mixture of the metal oxides, from the black mass, basically, because nowadays the graphite is, nowadays it's very critical, so people are really taking care of the graphite, trying to recycle it. But earlier, a few years ago, there was still enough graphite coming from China, and graphite was not really, they didn't focus on the graphite. So what was done was after when it went to pyrometallurgical processes, they used the graphite more as a reducing agent for recovering the metal oxides. But because China closed down their graphite export, or basically they limited it a bit, so then Europe came to think that, okay, we really need to have a look at this. And then, so the first plus of this process is that we recover the graphite, and the second plus is that afterwards, so the underflow project, which contains the metal oxides, usually follows then and goes to the pyrometallurgy, hydrometallurgical processes like leaching and so on. And those processes are much more efficient when the graphite is not there anymore. Because in those processes, graphite is more of a inhibitor, let's say. So this is also a second plus if we extract the graphite beforehand.
Okay, thank you, ma'am. Ma'am, it's a very nice session. I gained so much information from this webinar, and thank you so much, ma'am.
Thank you.
Thank you.
You're welcome.
Yeah, we are glad that it helped to gain some information. That was the focus. That was the aim of this.
Okay, I think that is the last of our questions and hands raised. So I think we are overrunning a bit, so apologies to anyone who maybe had to push another meeting. But so I think we will close up there for the day. So thank you once again so much to Johanna and Annette for being here today to share their insights with us.
Yeah, thank you so much for having me here to give me the chance to present. And of course, yeah, everyone can always contact me whenever there are questions. So
yeah, or us. Yeah, we are still in contact with each other. Yeah, and thank you for everyone's time. Thank you.
Yes,
thank you, John, also hosting.
Okay, I'll finish by saying yes. If you do have any queries, please do get in contact with us at marketing@surfacemeasurementsystems.com, or you can email us at science@surfacemeasurementsystems.com, and we can put you in touch with either of today's speakers to discuss this further. Please do remember to check our website at www.surfacemeasurementsystems.com for other upcoming educational content. And just to let you know, this session will be loaded to our YouTube account in the next few days. So if you maybe didn't catch the start or wanted to revisit any of the points raised, that will be loaded there. So just you can access that through our website. So keep an eye out for that. Thank you all once again for joining us, and we'll see you next time. Thank you.
Thank you.
Thank you.
Have a good day.
Too.